Alright, let's dive into one of the biggest head-scratchers in electronics. Seriously, it's a paradox that seems to fly in the face of everything we know about circuits, and it stumps people all the time. Think about it for a second. A capacitor is, by definition, an open circuit. It's a physical gap, an insulator, placed there specifically to stop electrons from crossing. So how in the world does an alternating current, which needs a complete path, seem to flow right through it like it's not even there? Let's crack this open. Quick refresher so we're all on the same page. A capacitor is basically two metal plates with an insulator sandwiched between them. If you connect it to a DC source like a battery, it charges up and then, bam, the current stops. Dead end. An open switch. Exactly what you'd expect. But with AC, the rules change completely. The first big clue isn't hiding inside the capacitor itself. It's all about the nature of alternating current. This is the secret of the sine wave. DC is a steady, one-way push, predictable and constant. AC, on the other hand, is always moving. The voltage rises smoothly to a positive peak, falls back through zero, dips to a negative peak, and then repeats this beautiful cycle over and over again. And that rhythm changes everything. So how does a capacitor handle this constantly changing voltage? It tries to keep up. As the voltage rises, electrons pile onto one plate, charging it. But just as it settles in, the voltage starts falling, and those electrons rush back out. Then, when the voltage reverses, electrons are pushed onto the other plate, charging it with the opposite polarity. This cycle, charge, discharge, reverse, discharge, happens thousands or even millions of times per second. Here's the big aha moment. Not a single electron ever jumps across the gap. It can't. But this constant back-and-forth sloshing of electrons on both sides of the capacitor creates current everywhere else in the circuit. The effect of current is there, even though the path inside the capacitor is technically broken. So yes, current effectively flows. Now, here's where it gets really interesting. In a simple resistive circuit, voltage and current are perfectly in sync. They rise and fall together. Best buddies. But replace that resistor with a capacitor, and something strange happens. The current gets ahead of the voltage. In fact, one of the most fundamental rules of capacitors is this. Current leads voltage by 90 degrees. Why does that make sense? Because current is greatest when the voltage is changing the fastest, and that happens right as the voltage crosses zero. And when the voltage reaches its peak and stops changing for an instant, the current drops to zero. Now, does the capacitor just allow this current without resistance? Not at all. A resistor provides resistance. A capacitor also opposes current flow, but in a completely different way that only exists in AC circuits. This opposition is called capacitive reactance, abbreviated as XC. Even though it's a different physical phenomenon, we still measure it in ohms. And here's the cool part. Capacitive reactance isn't fixed. It depends entirely on the frequency of the AC signal. The formula is XC equals 1/2 pi FC, where XC is the capacitive reactance, ohms. F is the frequency, hertz. C is the capacitance, farads. The key takeaway is this. Because frequency is in the denominator, reactance is inversely proportional to frequency. As frequency goes up, reactance goes down. At high frequencies, the voltage changes so fast that the capacitor barely has time to charge. It can't build much opposition, so it behaves almost like a short circuit. At low frequencies, it has plenty of time to charge fully and push back hard, acting more like an open circuit. Let's make this real. Take a 220 nanofarad capacitor. At 1 kHz, its reactance is about 723 ohms. Increase the frequency to 20 kHz, just 20 times higher, and the reactance drops to around 36 ohms. Increase the frequency by a factor of 20, and the opposition drops by the same factor. The capacitor becomes more and more transparent to current as frequency increases. And this leads to a powerful idea. If a capacitor allows high frequencies to pass easily while blocking low frequencies, what can you build? Audio filters, equalizers, signal shaping circuits. This isn't a glitch, it's a feature. And it's one of the most powerful tools in all of electronics.